All right, let's take a look at vertical asymptotes. Let's start by considering the function f of x equal to 1 over x plus 2. Notice the behavior near x equal to minus 2. The line x equal to minus 2 is a vertical asymptote of the graph of f. Definition: the line x equal to a is a vertical asymptote of the graph of f when f of x approaches infinity or f of x approaches minus infinity as x approaches a, either from the right or from the left. Now we'll be doing a lot of work with that. Let's get a definition of a vertical asymptote of a rational function. Notice here we've written out polynomials for n and d. The graph of f will have vertical asymptotes anywhere that the denominator equals 0 but the numerator doesn't. We'll talk about that in the very last part of this video. So let's do some examples here. We've got f of x equals 2 over x minus 3. X minus 3 equals 0 at x equal to 3. So x equal to 3 is a vertical asymptote. Notice the function can't be defined at x equal to 3. We cannot divide by 0. Remember, remember, remember. All right, let's look at another one. F of x equals x over x squared minus 7x plus 12. Need to factor the denominator and see where it equals 0. When we factor it, we get x minus 3 times x minus 4 equals 0. So we get x minus 3 equals 0, x minus 4 equals 0, x equals 3, x equals 4. These are both vertical asymptotes. In other words, the function is going to approach them, but it will never cross them. A function will never cross its vertical asymptotes. Let's try another one. X minus 1 over x squared plus 4. Aha! In the real numbers, x squared minus 4 never equals 0. So this means that this function has no vertical asymptotes. This will happen every now and then. Now, the next thing we want to look at is values for which a rational function is undefined. In other words, the denominator is 0. These result always in a vertical asymptote or a hole. So let's look at holes. Let's consider this function, f of x equals x squared minus 9 over x minus 3. Function's undefined at x equal to 3. But notice when I plugged in values here, that when I would get to x equal to 3, it seemed to jump over 6. However, notice as x approached 3, f of x got real close to 6 on both sides. We're going to discuss that in calculus. We're going to notice that we have a limit occurring there. So let's draw a picture, and notice when we draw a picture, if you squint real hard, you're going to see a hole, and in just a minute, that hole is going to be circled. Take a look at that. That's very important, because in this case, we're going to say that a limit exists even when the function doesn't.